Okay, so we're back again with some more examples from chapter 6 this time. So this problem we're going to look at a roller coaster and we're going to try to answer a couple different questions. So the first question we're going to answer is, okay, so here's a roller coaster. You've kind of just got like one dip we're going over. It looks like it's 40 meters tall, and they're asking us what's the speed at the bottom. So I think you could do this with kinematic equations, but since the motion isn't just in one dimension, the vector analysis would be quite difficult. However, if you use the law of conservation of mechanical energy, not like the whole law, but just the mechanical conservation law, then I don't think this problem is that bad at all. So I think the question is first, of course, what are we looking for? Well, I think we're looking for the final velocity, at least in terms of from the beginning to this point at the bottom of the hill, right? Make that a little bit nicer. But we're looking at the final velocity at the bottom of the hill here, right? In theirs, they called that V2 or the second velocity, and the first velocity would be up here, or V1, which is 0. However you want to say it. I'm going to use V2 since that's their notation. Okay, so let's plug in what we know. Here's the kinetic plus potential at the beginning, time 1, and kinetic plus potential at the end, time 2. Okay, so we're plugging in what we know, see if anything cancels. We said the velocity at the beginning was 0, so guess what? That's gone. Also, the height at the end is 0, so that y2 is 0, so guess what? That's also gone. That's really nice. Now you just have these parts left. They both have an m in them, which we can divide out, so we don't have to worry about that. And we say, oh, yeah, we were looking for V2. So isn't V2 squared, put my squared on there, equal to GY1 times 2 to get rid of the 1/2? And then you just square root and you have your answer. So let's put our numbers in there and square root it all at the same time. So the square root of 2g is, of course, 9.8. And what is the height at the beginning, y1? That would be 40. All right, if you wanted to do some fancy dimensional analysis, I guess this is the square root of 9.8 meters per second squared. This is meters for 40, so then you've got meters squared over second squared. When you square root that, you get meters per second. Oh yeah, that's nice. Okay, I got too excited. You'll have to excuse me. So I put that in my calculator and I get 28 meters per second. Okay, so the second question is, at what height, now that's not like a time or anything, that's a level, where essentially will the roller coaster have this speed cut in half? So at what height? Is it going to be here, or where is it going to be? So that's asking for a y, so the final height. So like they're calling that y2. Okay, so we apply the same law, and we just plug in all over again, except this time the speed is cut in half. That speed that we just found of 28 is cut in half, so make sure you do that. That's a little bit sneaky, I guess. You get 14. So I'm going to put 14 right here. 14 squared, I should say. And take half that. And then I have plus, the m's all cancel out, right? So let's just cancel those out first. Plus, that's g 9.8. We're looking for that final height, so that's still right there. That's what we're trying to find. The velocity at the beginning is still 0. And we have another g right here, 9.8. And the initial velocity was 40. Or, excuse me, initial height was 40. So we just solve for y2. Easy stuff. Look how easy the law of conservation of energy makes this. So we do that with our calculator. I don't know, I'll write it out here and then put it in my calculator. 9.8 times 40 minus, what's half of 14 squared? 14 squared is 196, so half of 196 is 98. I'm going to divide by that bad boy. Lots of 9s and 8s, be careful not to forget. And you get y2 equals calculator, let's see, I got 30. Now, if you'd like, see, I said there's a lot of 9s and 8s and stuff. What if you had forgotten, for instance, because when I was solving this to prepare for the video, I looked at it and I said I forgot to divide by 9.8, and I think I got like 290 or something. This isn't 290. That just doesn't make sense. 30 makes a lot more sense for where this would be third. for where that speed to be half of what it is at the bottom of the hill. So just use some common sense there, yeah? Okay, let's look at another one. So in our book, this is example 610. I may have changed a little bit. But okay, so let's see. Okay, so imagine you've got a couple water slides. You could imagine different shapes of slides. For simplicity, we're just going to say one water slide is just a big fall, and the other slide has like kind of two falls in it, two little bumps. So there are people going down both slides. So if they start at the same time, we got two questions. At the bottom, when they get down to the bottom down here, which person is traveling faster? Well, I think this really tests to see if you understand conservation of energy. Because, remember, at any time, the energy is going to be conserved. In other words, potential plus kinetic have to add up to the same number, right? So they both have the same potential energy at the beginning because they're starting from the same height. Same gravitational potential energy at least. So if they both get to the same bottom part, remember, I think that it doesn't matter what path they take at all. If they're starting at the same height and ending at the same height, they should basically have used the same amount of energy. I mean, you can look at the equations if you want, but basically the answer is that they'll finish at the same speed. So the final velocity of both of them is going to be the same. Okay? If you really wanted to look at the equations, I guess you could say like, I don't even think I'm going to. I think that's sufficient for this. So part B says which rider reaches the bottom first. So even though their velocity when they get here is the same, maybe they get there at different times. So that's a little bit sneaky, but it doesn't mean that this is necessarily going to be the same. Are they going to get there at the same time? I think that if you tried this with your friends or just thought about it in your head for a second, you're going to realize that no, they're not going to get there at the same time. The thing is, when they reach this spot, they're going the same speed. It doesn't mean they reach that spot at the same time. And I think you'd realize that if you just thought about it for a second. So who's going to reach the bottom first? I think if you look at the diagram a little bit, you should realize slider or rider looks like one is going to finish first. It reaches the bottom first. Why is that? Well, yeah, I think if you think about the energy, once again, you'll understand. So notice, this guy's kinetic energy, which is really going to make the velocity faster, which is what's, kinetic energy is what's contributing to your velocity, is not going to change a whole lot over this whole part, right? Until he gets about, well, he or she gets about right here, most of his or her energy is still potential. Then it quickly transforms to kinetic energy. But the problem is, this little guy right here, by this time right here, has already changed a lot of the energy into kinetic, which means he's going faster and he's going to be way down here while this guy's still fumbling around up here, kind of. And then once again, you'd say, well, maybe this guy will make up for it right here, but no, I think this guy's got the lead, and then he's just going to maintain that lead. Now, when they get to this spot, they're going to be going the same speed, but this guy's going to get there way before this guy. He's probably still going to be up in this area. Okay? Let's look at one more example today. This is about a dart gun. So let's say we've got a dart gun and the dart's kind of squished back in the gun. The question is, what's the velocity of the dart, like when you shoot the gun, basically? It says, what's the velocity of the dart as the spring expands to its normal length? So it's compressed at the beginning. There's its spring constant. And it's compressed by 6 centimeters. The dart, this looks like a pretty heavy one, actually, 0.1 kilograms, so that could hurt someone. But anyway, so it's compressed 6 centimeters, so when it fires and that compression goes back to its natural length, how fast is the dart going? So again, I think they're asking for like the final velocity or the second velocity here. The initial velocity is just it's stuck back in there, so that's going to be 0, isn't it? So you can just say, oh, yeah, this is 0 again. Right? This is not the gravitational form of the conservation of energy, but the elastic form. You notice that you've got the Hooke's law type of thing going in there for elastic potential energy in both the starting spot and the final spot. Okay, so I think one thing I've got it kind of in green here to remind us is that we've got two things going on in this problem that we have to be careful of. The first one is the coordinate system, and the second one is, do we have any sneaky units? So mostly, I think the coordinate system is going to be the issue. So where should we put our coordinate system? This is only one-dimensional motion, so I'm going to draw my line like this. And I think it's your choice where you put the coordinate system. I'm just going to say that this is the origin right here. So then this is a backwards compression, right? So the second position, in other words, the second x value, this is x equals 0. So that means this is going to be 0 right here. So that's going to go away. The first x position is backwards 6 centimeters. So the first x is backwards, or a negative 6 centimeters. And then we've got a half of 25, or is that, no, 250, excuse me. Half of 250 multiplied by that first position, which is back here. Let me get a different color. Back this way, 6 centimeters, right? So there's the other thing, the units. What is 6 centimeters? You could do a quick conversion if you want. That's one we should probably know, right? What is 6 centimeters? That's going to be 0.06 meters. You got to be careful of that. That's one that'll get you. So if we're going backwards, that's negative 0.06 meters, and it's squared, equals half the mass, which we said was 0.1. That's in kilograms, so we're good. And we don't know that velocity. That's what we're looking for, and we should be able to get it. So let's do a little bit of easy algebra. So the final velocity v2 is the square root of, what do we multiply by 2? So those halves will cancel, won't they? Let's cancel those bad boys right out. And you divide by 0.1. So what is 250 divided by 0.1? Yeah, we should be able to do that really, but you can get 2,500. 0.6 squared. I don't even really have to worry about the negative this time, luckily, because of the squared. It's just going to be 0.36. And what do I get from a calculator? Oh, 0.06. Whoops. I had a mistake. My velocity was too big. It said 30 meters per second what I got, and I said a dart gun. Unless this is like a Hitman's dart gun, it's probably going to be less than that. So that's how I caught my mistake. 0.06 squared. 0.0036. That could have been a bad mistake. Yeah, there we go. That's more like it. 3. So the second velocity is 3 meters per second. That makes sense for some kind of kid's dart gun. Now, I guess this could have been a real dart gun, and then in which case a bigger velocity might make sense, but not for a kid's dart gun. That has to do with the spring constant, how powerful the spring is, and that kind of thing. Okay, so hope you found this educational.